Okay, so hello, as mentioned, my name is Micha Hafner. Together with the supervisor Marko Buchanec, we prepared the work with the title towards a decision support system for project planning, multi-criteria evaluation of past project success. Even I have to read that. It's a bit long, but let's see what is behind this title. First, we will discuss topic, problem, and goal. Then the data preparation and analysis will be described. Decision modeling will follow. Decision support system plan will be shown. Preliminary results testing will be shown, and with the conclusions. What is important here is that this is work in progress. We don't have the finalized solution here, but what we will see here are the major steps of the decision support system. As mentioned, topic of the work is civil engineering, civil infrastructure. Before the construction of the infrastructure starts, there is the design phase, and we have different type of buildings. Here you can see 3D models of tunnels, bridges, or high-rise buildings. These models are usually produced during the design phase. This is the, let's say, requirement that we finish the project. Some sort of models are usually normal, and we can also have very simple infrastructure like this canopy. So the work included in the design phase can be very diverse, very different, but at the end we finish the project with deliverables that are handed to the client. So all the work from the design start to deliverables handled are considered as project work or the project itself. Typical examples can be building permit, geotechnical exploration, and so on. So all the work is related to the project is included, and it needs to be somehow managed, like how many subcontractors we will have, how much employees we will involve in the processes itself. So this is quite, let's say, complicated task, which can end with very different deliverables. As you can see from the picture, it can be very thin map or really a lot of files handed to the client. The problem is currently that this is somehow dedicated to the decision maker, which is usually project leader or project management, and thus very susceptible to decision makers' experiences or knowledge he or she have. The goal of the work is to collect all the data. We have very let's say, thorough IT guy who collected all this data from the year about 2000 or something, or something like that. So we have about 4,000, a little bit more than 4,000 projects already in the database. So I somehow gather this data and see what we can do, or we, of course, with the mentor supervisor. And another goal is to make the concept, design, and tools for decision support system in the company for the decision makers. Data preparation and analysis, as mentioned. Yeah, 4,700 projects are collected. Then followed the process of data cleaning, outliers removal, data imputation, and sensitive data and information removal. This is very important topic because we don't want to reveal too much sensitive, or not too much, but no sensitive data. This is also the reason, as you will see later in this example table on the left, all the values are scaled on the range between 0 and 1. So we doesn't operate with real numbers. because the reason is obvious. Here is the look on variables which we obtained at the end. I forgot to say we reduced the number of projects and variables. Also, we ended with 27 variables in the database at the end. These variables explain the workflow of the project, the pauses of the project, how many subcontractors are involved in the project. Also, how many hours, how many employees was involved. Also, monetary values related to the project was included. We can observe this data in very different ways, but this is example of a distribution of the variables that we have in the database. On the x-axis, you see the variables. Here you see the distributions. I won't go into details because there are many different possibilities or many different techniques was used. What we didn't have in the database was the success information, the information of the project success. So we need to come out with the system to evaluate the success of the project. What was the goal is to come out with the model with which we can evaluate the finished projects as well as the new project. Maybe I didn't point out this well. Now I'm talking about finished projects, but everything that is done for the decision support in relation to the new project that comes to the company. So we need the model that would enable us to evaluate the project success. And the solution was, or final decision was, that multi-attributed theory model would be used because it's multi-criterial, it's hierarchical, and also it's weight-based, and this is the model which we made for the task. You see at the top node is overall project success. Leaves are direct parameters from the database, and the weights are such that each parameter is equally important, so we can track the success or functionality of the process better. This model was done based on discussions in the company or communications, interviews, and so on. This scheme shows how we evaluated all the finished projects in the database. Maybe I wouldn't go into details now. So the idea is that we have to evaluate all the finished projects in the database. In this way, we obtained 5 additional success scores for each project. So this can be seen as derived variables for the next components in the data support system. And here you can see the stars are showing decision-making parameters that are in the databases. This is the decision support system plan. What was discussed up until now is this part here, how we evaluated the finished projects and also the evaluation model, which is also necessary to evaluate the new project, which comes to the company. So we have here input. These are the characteristics or properties of the new data information of the new project. Here is another component which enables the extraction of the knowledge or the data obtained in this step. We tested few machine learning methods to obtain the output. And these are new project parameters which are shown to the user as a support for the decision making. The system, of course, is just a support, and then it's decision makers' responsibility to accept the final solution. And here you can see one of the possible ideas. What can we do with this evaluated finished project in the database? We can do clustering. And here you can see clusters. These are mean values of each cluster. Here are the variables. In this case, we obtained 6 clusters, and these clusters already tell us a lot about the projects we have in the database. But of course, all the clusters are not relevant to our new project. So here we have some boundaries, and we can see that only 4 clusters can be related to our new project from the database of evaluated finished project. The next idea would be to obtain similar and successful projects. So we reduce the number of finished projects in the database and observe what is going on in this database. In this case, with some boundaries related to project similarity, we obtained 170 projects which are similar and also successful. So here you can see success score needs to be higher than some value. And when another, let's say, development of this idea could be to cluster the successful and similar projects again and observe this how this segmentation can offer additional information for the decision making. And here you can see these 3 clusters, these parameter values of these 3 clusters that in this result can be also used in further steps. So the conclusion, we can conclude that this approach enables the decision-making support. So this requirement or goal was achieved. We can evaluate the success of the finished project as well as a new project. This success evaluation was very important. We can relate the new project to the projects that we already have in the databases, and the methods used enable us to make informative decision support for the decision maker. Thank you.
You said that you use machine learning as well. So which methods do you use?
Clustering. Yeah, I have shown clustering.
Okay, so unsupervised.
Unsupervised.
Yeah. Did you consider to use also some kind of supervised?
Yeah, it is planned, but the performance on the level that it was tested is, let's say, not to be shown. We need more work to achieve good performance of supervised model.
And which kind of clustering method?
Regression model.
Clustering.
Hierarchical clustering.
Did you also consider just visualizing this project space with some other tool for the visualizing multidimensional data, such as, let's say, multidimensional scaling, or let's maybe Disney or UMac? Did you actually
Yes, that was very important task when we decide upon the variables chosen for the model. When we need when we was figuring out which variables that was in the final database, we tested these approaches, and also graphs was made, and information gains was also calculated, and PCA was also included to see which variables are more or less important and relevant for this final database. Because here, maybe I didn't mention, we started with 39 variables in the database. This is a lot. So then we have to reduce this number, and then we went further on with the regression model, and this is related to the previous question.
Yeah, one more question.
So yes, about the weights in the decision model, you showed that three, and there were all weights of 0.5, right? So I wonder why that I guess in practice, expert personal preferences. Was that not enough time, or we plan to refine this in the future? Because of course the outcomes depend on it.
Exactly. If we change these weights, we obtain a different result. As mentioned, these successful projects are then different. We have these numbers now because it's easy to check the results. But later on, if the user would, let's say, prefer better workflow, these numbers can be changed here, ways, or project poses would have some different importance, then this could be changed, and different results will be given for the user.
Okay, I'm afraid we have to move forward, so thanks. And let me announce the next speaker, Taya Kuzma. Will be presentation about Panda Chat towards the benchmark for Slovenian REG application. Please, Taya.
Hi everyone, I'm Taya Kuzman, and I present work that was done in collaboration with my colleagues from the PC7 company and the Josef Stefan Institute, Tanja Pavlovska, Urbana Rupnik, and Primož Cip. So what is RAG? RAG is retrieval augmented generation, and this is a methodology to enrich a text generation used by which is done with large language models with document retrieval. So we provide the large language models with documents from which the models provide the answer. And this method is used to mitigate the well-known hallucination by the LLMs. And as we can provide the source based on which the LLM's answer is generated, it also provides some explainability. As it is despite being fairly new, it's already been widely adopted in various applications, including in chatbots that use customers' data to provide answers to the customers using LLMs. However, evaluation for these models is lacking, especially for less resource languages. So here are some challenges with the benchmarks for the RAG methodology. First, the RAG pipeline can be used for various applications, so we also need different tasks and benchmarks to test the system. And in our case, we used the attributed question answering task, where we evaluated the retrieval component based on its capability to retrieve relevant sources for the question that is posed to the model. And secondly, the benchmarks are currently available only for English and Chinese. So we developed a Slovenian benchmark, and we also introduced a methodology based on which we can create similar benchmarks for other European languages. And thirdly, one other problem is that most benchmarks are created using synthetic data, so just using LLMs to generate questions and answers. But by that, we can only access the knowledge that is already present in the LLM. So we might not be able to find non-standard language, dialects, or questions that are, or topics that weren't already used for training the LLM. So, but we used a methodology which is based on web corpora, so web text collections, and this methodology enables efficient development of non-synthetic real-world data. So in this presentation, I will present the Slovenian RAG benchmark based on a Slovenian test dataset, a semi-automated methodology to develop such benchmark. And then we will also evaluate the retrieval and indexing component of the RAG system on its capability to retrieve relevant sources for the question. And here we will evaluate different embedding models and different parameters. So what is RAG? The RAG pipeline consists of three main components: the indexing, retrieval, and text generation component. And first, we provide the system with a document collection. Could consist of 1 up to thousands of documents. And we have to segment the document into chunks of fixed length. And then these chunks are then converted into numerical representations, also known as embeddings. And for this, we use the embedding models, which are large language models. And then we store these embeddings into a vector database. And then when we ask a question to the system, the question is also embedded into numerical representation. And here in the retrieval part, a semantic search, also known as dense retrieval, is performed which finds the closest embedding amongst the document embeddings that is the closest to the question embedding, and this is based on cosine distance. And then when we find the closest documents, could be one, we can decide that we will only use the top one closest or more. We pack everything together into a prompt, and in the prompt for the large language model, we provide instructions, the question, and also retrieve text. So we basically say to the LLM that it needs to answer to the question based on the text that is provided. And here we will evaluate the chunk size, which is important because if we have very small chunks, we might have more details in the embeddings. The embedding models, which create different embeddings, and also a number of retrieve sources, which will be provided into prompt. Because if we provide, for instance, top 5 retrieve sources, the probability that the accuracy of the answer will be high is bigger. But at the same time, we will have a longer prompt, and this might incur some costs. So moving directly to the dataset, we developed a Slovenian dataset of around 200 instances, and one instance consists of a question, answer, and the entire text. And here, the texts are being segmented into chunks and embedded. It is freely available, and what is nice is that the pipeline for development of the dataset that I will present is easily expandable to other languages. Inter alia, the Makoko genre corpora have been recently released, and they are of exactly the same format as the corpus that we used, but comprise 13 languages. So this means that the methodology can be easily expanded to all South Slavic languages, but also Icelandic, Catalan, Turkish, Ukrainian, and other languages. So this is how we developed the dataset. We've taken a web corpus. This means a text collection that was collected from the web. And this corpus was a nice choice because it comprises a high quality content. It is one of the largest and most recent text collection for Slovenian. And as I said, there also exist comparable corpora for other languages. Then what is also nice is that it comprises metadata on the genres, so text types for each text. And based on this, we decided to extract only text for which we somehow expected that there will be objective questions and answers, because we didn't want dialogue that could occur in news text, for instance. So we took texts that were marked as information, explanation, instruction, and legal, and then we simply automatically extracted text that contained questions and answers, leaving us with 80,000 texts. Then we created a sample and did a simple manual review to see which instances comprise nice questions and answers. And we stopped when we got 200 instances, but we could just go on and have a larger data set. So then we evaluated the indexing and retrieval component to see whether it is able to provide relevant sources when we pose the instance, the question. And this is the task of attributed question answering. And the metric was simply accuracy, so percentage of questions to which we were able to obtain the relevant source. And here we analyzed different embedding models. We used 8 open and closed source models, the size of documents, chunks, and the number of retrieved sources. If we look at the impact of the chunk size, here the size is in tokens, which is used by the models, and this is essentially sub-word unit. Could be the entire word or a word chopped into smaller parts. And here we can see that smaller chunk size, doesn't matter which model we use, smaller chunk size provides better retrieval accuracy. And here, when we basically embed the entire document, this can even result in a drop of results in more than 15 points in accuracy. So this confirms that smaller chunk size of optimally 128 performs the best, as we presume that this means that it consists of more details and is more similar to the question. So if we look at the retrieved sources, the idea is that there's some cost efficiency if we use less sources, if we provide to the text generation model only top 1 hit. But this could also mean that there's a larger possibility that this top hit won't be the right one, especially if we have very similar text in our text collection. So we looked at how many retrieved sources do we need to provide to gain the best accuracy. And we've seen that for most models, we reach a plateau beyond 2 retrieved sources. So it makes, and even with 2 models, BGE M3 and MEA5 large, we can achieve perfect retrieval accuracy when we use 2 retrieved sources. So as the cost efficiency is important, we can use 2 sources, and that's already will get the perfect results. So using the optimal parameters that I presented, we also looked into which embedding model is the best. And we can see we used 5 different open source models available from Hugging Face and 3 models from the OpenAI company. And we can see that the 2 open source models, BGE M3 and ME5 large, are actually capable of perfect accuracy. And the third one is the OpenAI 3 small, which is also provides good results and is useful for people who do not have access to GPU resources. But if you also need a model that is as fast as possible while also very accurate, we can look at the ME5 base, which is much faster than the other better performing models, but has almost the same performance. So to conclude, we present a novel benchmark for Slovenian RAG applications, and we've shown that 2 open source models are actually capable of perfect accuracy in retrieval, and we've also shown what are the optimal parameters, so small chunk sizes and up to 2 retrieved sources. In the future, we aim to do a broader evaluation. These were only the first steps. So first, we want to also evaluate the text generation part, So whether it provides accurate and fluent and also useful answers, and also expand the benchmark in this using this methodology to other languages. That's all from this.
Questions, please? Yeah.
So yeah, thanks for nice presentation and very useful benchmark. So I was wondering now the RAC is getting increasingly large pipelines, so different components will be interdependent. So did you observe any such interdependency between prompt and retrieval?
So if there's independency between prompt and
So for example, might be the retrieval mechanism might be dependent on the prompt.
yeah, so in this part of the evaluation, we actually evaluated only up to this part. So we've changed chunks and embedding models and number of sources. But then here we looked at what the semantic search outputs. So the number of retrieved sources, the actual like this. No, here it is. Just a document ID of the retrieved sources, and then just calculating accuracy based on whether the retrieved sources are among the ones that are correct. So here there were actually no evaluations of the prompt or the LLM because we looked only basically at the retrieval part.
So this, I mean, the semantic search, I mean, the IDs of the document, these were manually checked.
Whether they're correct.
Other questions?
Okay, so you've shown us 7 or 8 different embedding models that you used. So why did you choose exactly them?
So for the OpenAI models, I use those because they're very widely, the OpenAI products are very widely used, especially as they're very easily integratable using the API. And those are the 3 models that are the embedding models from this company. And for the other 3 models, so BGM3 and GT base and the 3 versions of ME5 model. These were chosen because based on the MTAP benchmark. So there's some benchmark on Hugging Face, which evaluates embedding models. And these were among the best performing. But I also looked at that this benchmark is available for different tasks for not Slovenian, but there's Polish and Russian. So I looked at these 2 languages, and I also looked at models that were fairly smaller. So for instance, you could also use models like Mistral or Llama to do embeddings, but they are much bigger. So we stayed with the smaller models that can be easily run on a smaller GPU.
Okay, the second part of my question actually relates to this. Which vector database did you use?
This was actually just the default vector database of the Llama index library. So it was nothing like a special product, and the embedding model, the embeddings were just stored on a folder in our computer.
Because I know that some vector databases, for example, Schema, they actually include 5 or 6 different embedding models. And I was wondering if you make any comparisons and if they were significantly worse than.
Yeah.
So did you or did you not?
No, I know there are a lot of different vector databases, and I've experimented with some, and the results were different. So it seems that also just using the same pipeline but a different vector database changes the results. So that's why we just stayed with the default option, but it would be interesting to look into it.
Okay, thank you. The time's up, so thank you very much. Our next presenter is Lazar Djokovic about sarcasm detection. So, please.
Okay, so I'm Lazar Djokovic. I'm from Serbia originally, but I did my bachelor degree here in Ljubljana, Slovenia. Now currently I'm enrolled in the Erasmus Mundus Joint Master in AI. I'm spending this semester in Barcelona, but my plan is to come back to Ljubljana for my second year. My co-author, Marko Robnik-Šikonja, you probably know him. He is a professor at the University of Ljubljana Faculty of Computer and Information Science. And we tackled the problem of sarcasm detection in less resource languages. So to start off, the Slovenian portal Franci defines sarcasm as a critical, derisive, or caustic attitude towards someone or something, usually manifested in the words, but the use of words that convey the opposite meaning, opposite of their meaning. The thing we can see from this definition is that one of the defining features of sarcasm is sentiment flipping or inversions. They can be of several different forms. They can be, for instance, positive to negative. When we say, I don't know, I just love being stuck in traffic or hot weather. Or they can be negative to positive, saying I, for instance, hate my super fast brand new car. They can also be neutral to negative. For instance, when somebody says something that's unbelievable and we say, yeah, right, and I can fly. Sarcasm generally is a very hard problem because of this ambiguity, and even people sometimes struggle to classify it with very good accuracies. So they usually achieve on one data set, the sarcasm data set, which we'll see shortly, people get 78% accuracy. So one of the motivations for researching sarcasm is its use in sentiment analysis, because people's reviews of products could be sarcastic. This could thus induce errors in sentiment analysis tools, and companies might not get the true opinions of their users. So our goal here was constructing a supervised sarcasm detection model. We explored existing data sets, which were mostly in other languages. Specifically, they were not in Slovene. These data sets can be very large and noisy, like ones that are created by scraping Reddit or Twitter, or they can be smaller, more refined, handcrafted, and usually more expensive. On some of these data sets, large language models perform better or worse based on the type of data set it is. These noisy data sets can get very high accuracies, but they're obviously not representative of true sarcasm. On the smaller, harder data sets, some language models up to 1 billion parameters get an F1 score of around 0.6. Of course, our question was, can we beat that? We decided to use a translate-train methodology. So we used neural machine translation. We chose one data set that we thought of as being good. We'll see what that means later. This was a data set in English because English is very well resourced. It has quite high quality data sets. We translated it into Slovene with multiple machine translation models. Well, actually, we chose one. We'll see which two did we take. We chose one T5 model trained specifically for machine translation, and we chose one larger foundational model, which was much larger than a T5 model, and we compared their results. We decided to fine-tune various array of various different LLMs after that to classify these translated text. We chose models of differing sizes, architectures, and the way unsupervised training approaches, so how they were trained in the beginning. We combined these models in the end into ensembles using two methods: stacking, where we used L2 logistic regression, and mixed and regular voting. The models we used were the MATLAB 400 10 billion machine translation model from Google. It's a 10 billion T5 model, so text-to-text transformer. It's 10 billion parameters. This should be quite a bit smaller than OpenAI's GPT-4o model, which was the best available model at the time writing the paper. We don't know its true size. It should be a lot larger than 10 billion parameters. We will see how they translated the data set later. And for the downstream task of actual classification, we chose a plethora of different models. Some trained specifically in Slovene, so monolingual Slovene models. Oops. Others multilingual models of differing sizes. Some are open source, others are closed source. And yeah, also differing architectures. So some were encoder models, others were generative or just decoder models, transformer models. The dataset we used was the iSarcasm eval dataset. This dataset had instances in English and Arabic, but we chose to focus on the English ones. The dataset was created by asking authors on Twitter to submit their sarcastic tweets themselves. These tweets were then filtered. 2 annotators were brought in to check if the annotations make sense. When there was a tie between the 2 annotators, a third one was brought in as a tiebreaker. The translations we got from T5 and GPT models there was quite a big quality difference. We assessed this by just looking at the examples and seeing that the T5 model, even though it's trained from machine translation, wasn't large enough to capture all the intricacies of languages such as English and Slovene. It would fail to translate some words that it didn't understand. It also failed to keep the original structure of some examples. So it would drop text which it didn't know how to translate, for instance, in this second example. Whereas the GPT model performed much better. It usually kept the structure and meaning of the original examples. And it even kept like the punctuations and capitalizations of letters the same. So we kind of decided that the GPT model's translations were generally just better. The dataset was unbalanced. It had a ratio of 1 to 3 sarcastic and non-sarcastic instances. This resulted in some of the smaller models defaulting to just the majority classifier. So we decided to balance the dataset, and we only kept the sarcastic and an equal number of non-sarcastic examples. Then we divided the dataset into train, validation, and test splits for later training. So the actual performance of the classification models was fairly interesting. Our hypothesis was that since sarcasm seems to be a kind of hard task, that generally larger models would always outperform smaller ones. However, we saw that the monolingual Slovenska model actually outperformed the slightly larger multilingual BERT and XLN models. We also saw that by using LoRa or quantization or other techniques which try to reduce the computational load of training transformers, these techniques usually didn't result in good performance. So it kind of seems that we really need the full expressive power of a transformer model to achieve good results in sarcasm. We also saw that the best performance was achieved by fine-tuning using the OpenAI's API, the GPT 3.5 Turbo model. This almost reaches human-level performance, but falls short by a small amount. However, we can start to approach this accuracy by using some open source models like Cloud 3.1 from Meta, if we have the GPU resources for them. In the end, we also noticed an interesting phenomenon where the accuracy of F1 scores actually diverged in these models. So we saw that, for instance, for the Llama 3.1 for a 5 billion model, it classified more instances as positive than negative. This might be due to skewed distributions in the original training set, or it could also be due to its instruction following fine-tuning, that they might be biased towards answering yes rather than no, but this would be a very interesting topic to research in the future. Do language models become kind of yes men when they encounter hard problems which they don't exactly know how to solve? We then used all of the models we trained individually and combined them into differing ensembles. We noticed that when we used logistic regression and L2 logistic regression specifically, we did manage to improve performance slightly. So there is still some improvements there. However, it does seem that most of the larger models do kind of learn the same things. So they agree most of the time. Hard voting and soft voting didn't have any performance benefits, even though some papers in sarcasm detection claimed that they achieved the best results with these kinds of ensembles. We also tried mixed voting, but that also didn't improve the base performance of the models at all. L1 regression also showed that we can just kind of take the 5 best models. That was our motivation for choosing the 5 models for hard and soft voting, but it didn't improve the base performance, so we didn't include it here. So to conclude, we confirmed that sarcasm detection is a very hard task due to its natural ambiguity. We saw that larger foundational models, which are not trained for machine translation, still outperform some medium-sized models in machine translation, specifically for English to Slovene translations. We saw that we need very large models if we want to detect sarcasm semi-robustly, or at least on human levels. We saw that LoRa and aggressive quantization do degrade performance. And we saw that there is still some performance to be gained from ensembling. For future work, we would probably suggest the creation of specifically Slovene manually labeled datasets, possibly even creating sarcasm detection models for multiple languages. We would definitely explore the phenomena on the divergent F1 and accuracy scores by testing different hard problems, and other types of models such as mixed of experts, and even adding more context to examples, or adding other labels that could guide models in the direction of training. So
Interesting topic. Questions, please. You were the first.
2 quick questions. Thanks for talking. First, how do you evaluate the translation? You just manually check all the instances and maybe are evaluated how well the translation works?
We went over the translations manually. A couple of people looked at them. They were mostly evaluated by just the ones that were the same, but the ones that differed, the GPT model generally just had much better translations in those examples.
For the actual content of those tweets or whatever they were, did you exclude some that, I don't know, are not really understood in Slovene because some things don't translate between languages well? For instance, even the case you showed, bring on the owl or whatever, I don't know what that means.
We didn't do that because the data set was kind of manually checked, so it's pretty small. We tried to keep it as large as possible to capture the distribution of sarcasm as best as we could. But again, some future work which would focus more on data sets for Slovene could improve on this data set, definitely. This is not the best way that somebody would do this, but again, we would need some funding for creating a survey, a linguistic survey, which we could share and then obtain better data sets.
Thanks. We have one more question.
So I understand that sarcasm detecting is hard and therefore challenging as a research problem, but practically speaking, why would one want to do that? You mentioned some relation to sentiment. Can you be more specific on that?
Currently in the world, social media and generally the use of internet, it's all present. This anonymity that we got via the internet did kind of increase our use of sarcasm for whichever reason. Online and social media, on reviewing platforms, sarcasm is ever present. It's even more. Some papers suggest that it's more present today than it was 15 years ago. So sarcasm generally, it's around us. It affects reviews. It affects mostly websites and the data sets we're using for sentiment analysis and any other task, they're usually obtained via the internet. And since sarcasm is more prevalent on the internet, we really need to detect it robustly to be able to do other tasks, as well as to get actual opinions of users on the internet for whatever task it could be. For instance, on comments on news websites or for reviews of products. So its detection influences many other tasks in the field. That's why it's important.
And for one more question? Yes.
Thank you for a very interesting presentation. So regarding the prompt, did you use the same prompt for all the models? Did you do some prompt engineering experiments? What's the best prompt? Did you write it in English or Slovenian?
We wrote it in Slovenian, and we didn't explore different prompts. This was something that could also be improved in the future. We looked at the prompt engineering examples OpenAI had on their website, and we adapted those templates to our task directly.
Did you also explain to the model what is sarcasm and give some examples, or?
Yes, we did multi-shot learning. So we provided a couple of examples in the prompts, which were sampled from the dataset, manually translated and labeled. Yeah, we included those. Yeah, okay. Thank you.
Thank you very much. Our next speaker is Marisha Dias. Please. So the topic is speech to service, using LLMs to facilitate the recording of services in healthcare. Aha, so you are
Yes.
okay, I didn't know that.
Hello, my name is Marisha and this is Rolf, and today we are going to present you speech to service. So we developed two systems that could help healthcare workers like nurses and technicians to spend less time on overwhelming documentations and more time on actual healthcare of patients. So we developed two systems. First system uses speech recognition technology that could listens what nurses and patients say and writes down and checks out the actions that need to be done or have been done. And the second system is the recommendation system that predicts what needs to be done at specific time for specific patient. Now Rok will present to you first system.
Yes, so the speech to service system consists of three parts: the diarization, the transcription, and information extraction. So first we take a pre-recorded audio file, we put it through diarization to determine when a speaker has started and ended speaking. That was done by anode speaker diarization 3.1, unmodified. We then sliced the audio by those timestamps and passed each chunk to transcription. The transcription was done by OpenAI's Whisper medium English model. And the point of this is to construct a form of play conversation. So we have a speaker and a column and is line or turn. Then the formatted conversation is passed on to the information extraction part, which is just the 8 billion parameter version of Llama 3, which has been fine-tuned on a synthetic dataset of medical conversations. And the LLM then reads the conversations. It out of the context. It figures out what has been done or what has been mentioned, and then outputs a string, which is then programmatically interpreted as a JSON object, and from that we can read what has been mentioned in the conversation.
And now I'm going to present you a recommendation system. So when we got the data, we had a problem because it was a very limited data set. Because of the privacy laws, we only got patient's ID, care type, and service history. So we wanted to, that was quite a challenge. And as an attribute, we wanted to include care type, but it was not clear, not even expert didn't know that if the care type is the actual service provided. So firstly we done clustering. So we clustered the data, and care type represents how much assistance someone needs, from minimal help, that's care type number 1, to maximum help, that's care type number 3. So by clustering, we saw that patients with the same care type actually have same service patterns. There were slightly deviations, but this is caused by patients' temporary conditions. So actual care type aligned well with service provided. So then we started to build our recommendation system. We use a machine learning approach where we trained our models on 5 months data and calculating accuracy on 6 months. We tried different models like random forest, decision tree, neighbors, gradient boosting, naive Bayes, and CVS, and 5-fold cross-validation for fine-tuning. So at the end, we add additional recommendations with a Markov chain model, so our recommendation system could be better. Here we can see recommended services for specific patient at the specific time. And as we can see, the best model was Neighbors, which performed with 70% accuracy. Here I need to highlight that this is a multi-label classification problem where a lot of tasks are being predicted at the same time. So the overall accuracy is not the only one that is important, but we need to focus on accuracy where a specific tasks have been predicted also. Our model achieved 90% accuracy on predicting individual tasks. So in conclusion, these two systems could work together and could increase healthcare efficiency. So recommendation system with predicting services or tasks, and uses this information in speech to service pipeline. At this point, I need to highlight that we need to focus on privacy restrictions like GDPR and EU AI Act, because recording a conversation between nurses and patients involves privacy risks. That's why strict safeguards, clear data ownership, and limited access are needed. In the future, we will focus on system and model development while ensuring all data use follow strict legal rules and protect patient information. This is early work and further improvements are underway. Thank you for your attention, and if you have any questions, please.
Yeah.
Yeah, you mentioned as a motivation that this is the purpose is to decrease the administrative burden of nurses. But then in your recommender system examples, I saw things like recommending taking medication, checking psychological condition and so on, which I would argue is healthcare, which you said that, you know, they would have more time for healthcare. So are you recommending actual like, you know, health checkups and things like that? And if so, do you think your evaluation of accuracy is appropriate? Like, how do you ensure that the recommended service is the right one for the patient?
Yes, good question. So the recommendation system, it's not the system that could that could tell you what you need to done without the professionals. So nurses need to know what have to be done at the specific time. This is just a reminder, and so the unnecessarily visits could be prevented. Yes, for the accuracy, how we calculated was like we trained our model on the 5-month data and evaluated it on the 6th month. We have data for the sixth month, like what are actual tasks. So when we predicted them and calculate their accuracy.
Questions, yeah.
Okay, so since this transcription can also include, let's say, therapy or medication, so it can actually affect treatment. So did you make any discussions or consider should your product, if put in production, be treated as a medical device? And if it's a medical device, then at which level should it be certified?
Oh yeah, we discussed this a little bit, but this is like a proof of concept, so not it's not already a product. But of course, there must be a lot of discussion about how that could be used and what kind of restrictions are needed for use of the system.
Yeah, sure, because I mean, this certification is often bureaucratic and complicated process. So you actually need to be aware in which direction you're going to this time.
Yeah, of course.
I have one question, but, oh, sorry. Bogdan, go on, sorry.
Okay, so I have a comment, not a question. So overall, with administrative work, there's many professions. So I'm just thinking in research as well, where especially senior researchers have to do a lot of work with managing project human resources. So it would be very nice if we would have some help of this kind.
Thank you. So my question is more specific. I wonder about the classification accuracy. Is it necessary or how to deal with it? You mentioned it's a multi-labeled classification, and in my opinion, it really doesn't matter if maybe some actions are moved here and there and so on. So the question is, are all those activities of the same priority, so as to say, and is it really important that some activity is done at 18:00 and not at maybe 20:00 and so on? So how do you cope? How do you see this thing?
Yeah, thank you for this question. That's why we reported like the second accuracy, because of course for like this purpose, because we done this system for the nursing homes, and there is not it's not important if the breakfast is recommended at 7 or 8. That's why yeah, we reported another accuracy. But if this system could go on like in the hospitals or this kind of facilities, this maybe needs to be considered, and it's important at what time.
Well, it's just the matter of view, in my opinion. So, you know, some activity has to be done.
Yeah.
But it doesn't really matter if it is at 7, 8, or maybe it does matter, but it's maybe less important. Some activities are probably optional, but okay.
Yeah.
It's probably.
I agree.
The last chance for a question. Yeah, please.
Here you use, let's say, general classifiers for the recommended system. Why did you choose those and not some dedicated algorithms for recommender systems like collaborative filtering or something that's traditionally used?
Yeah, so I mentioned that we had a problem with like limited data, and we were wondering what kind of attributes we can actually use, because we had only ID of patients, care type, and service history, and it was very challenging to extract these attributes. So in the future, we want to get the data where we can do like more attributes and like disease and this kind of health data to predict like and do collaborative filtering and item-based and person-based recommendation system.
Yeah, I think it would make sense because KNN was the best performing one, and those are, I would say, most similar to KNN by design. So, okay, thanks.
Okay, thank you. You need to move forward. Our next speaker is Matthias Lucar. About predictive health related absenteeism.
So this is a joint work that I did with Alexander Pickida, who is currently doing his PhD in Germany. So unfortunately, he couldn't be here. Otherwise, he'd be presenting this talk. Okay, so what is absenteeism? It's a complicated word, but actually, we all know this term as a sick leave. And this is a chart showing absenteeism in Slovenia from 2014 to 2022, so in 9 years. And in this time, absenteeism increased by 50%, which was a horrible thing for me to see, actually. Now, what did this number mean? So absenteeism is measured in the percentage of or rate of the days absent from work. So absenteeism 0 means that you're at work every day. 1 means that you are not at work at all in the year, and all the numbers in between are just the percentages. So this means that in, let's say, 2022, about every day, about 6% of Slovenian workforce were at home, being sick or pretending to be sick. Okay, so this is obviously a serious problem for companies because this incurs additional costs, both in paying for the sick leave for short term, reduced production or service quality, depending on the company does, and also planning for these events because they need to actually overemploy people so that they'll be able to cover such absences. So this is a problem. Now, also in literature, this has been detected as a relevant field of research, also in computer science. So in, let's say, last 10 years, several papers were written using AI and ML techniques, but there is very little data available for this. And finally, most of the articles, they use data from Brazilian couriers. So it is something that is probably not relevant, let's say, for our circumstances at all. And what the results of such papers usually are, they focus on qualitative results, which sometimes seem to be very good, suspiciously good, and also on qualitative insights. So what are the contributing factors for, let's say, this absenteeism and so on. So we were lucky to get in touch with a large Slovenian tech company, which unfortunately did not want to be named explicitly. So that's just the company X. For now, we acquired data for a 6-year period, so from 2017 to 2022. All the data was anonymized and contains very little personal data, basically age, sex, and some social circumstances, like if the person is disabled or if they have children. So these are just Boolean flags. So it's actually very little identifiable data. Almost 14,000 instances. So one instance is data for one person per year. So divided by 6, this would mean about 2,000 people. And this data was actually pre-filtered, which is something I did not like, because they did not dare to export the data for higher management. So only for, let's say, normal workforce. Well, we had 49 attributes, so 48 were actually describing people, and one was the absenteeism in current year, in terms of this number from 0 to 1. And the target that we wanted to predict was next year's absenteeism. So this is the breakdown of the attributes. And as is usual in real life data, in real life situation, data was quite messy. It was never meant to be machine processed. So they had things like this. So for length of service, or in Slovenian, delovna doba, they were codes like this, and this means 8 years, 9 months, and 3 days. So things like this needed to be first detected and then discussed with experts there, with human resources department, and so on. Then there were also several other things we needed to use, certain encoding for other certain kinds of data fields and so on. So it was quite a lot of manual work needed. We tried to use LLMs for help here, but they did not help much because we needed to contact them for most of the things. So it was most of the work was done here. So this is the target variable, or absenteeism. As you can see, this is more or less as expected. So most people have absenteeism relatively close to 0. But what we notice is that if we're looking at a certain person, there can be very big difference year to year. So 1 year you can be healthy, next year you can, let's say, break a leg or go to an operation and stay at home for a few months. So there was quite a big variance. But year to year for the population, these differences were not very big. Actually, they were decreasing until 2020, and they're starting to increase. And especially notable is this increase in 2021, which may be related to COVID. We are not sure. It's no way to check it, but it may be related to this. Okay, this is another, this is the same, actually the same picture as before, but now the scale is logarithmic. And why I'm showing this is because of this part on the right hand side. So close to 0 or even close to 1 or even 1, they have about we have about 100 instances. So this would mean that about, let's say, about 20 people are permanently on sick leave. So obviously they do have employees like this, but there are actually not that many. First experiments with original attributes were largely unsuccessful, and it clearly became clear that they needed to be transformed into some different or augmented with expert knowledge. One such interesting augmentation, which actually raised a certain kind of attributes from unimportant to most important, related to employee evaluations, where we encountered the problem, which is quite similar to some problems in recommender systems. Namely, we also have some hierarchical structure of the company, and we detected that there were very big differences in evaluations depending on the evaluators. So there are some people who are also always giving 5s to the people they were evaluating, and some who weren't. So for evaluations, we subtracted evaluators' means, and we were able to do this because we knew who was we knew who was evaluated by a certain evaluator. Also, for some other thing, other interesting is this: some attributes had a huge number of values. For example, 40 or 50, depending the work position. They were obviously at first not very useful, but when grouped to work fields with just 3 groups, some interesting things happened, which I show you on the next slide. And also we did some correlation analysis with future absenteeisms, just to see in advance which attributes influence it the most. Now this is the representation of this work field. And the interesting thing is that, for example, in technology part, the absenteeism is very, very low. So it's less than 0.01. While, for example, in sales, it is about 3 times higher. So and in support, in user support, it's somewhere in between. So the actual question is why is this so? So it may be related to engagement or satisfaction at work, but also possibly on gender, because there are many more women employed in sales, so it may be more related to sick leave because of children. So, but still, it was an interesting result. Okay, this was a representation or visualization of the data space with Disney in 2 dimensions. The colors here represent absenteeism rate. So the darker the blue color is, the closer this is to 0.25, and after, so quarter of here, and after 0.25, everything was red. It's actually, you can see that these red dots are actually nicely spread out throughout the data. So it is obviously quite a difficult problem, but there is small cluster here on the left-hand side. So they all obviously they do have something in common. Now experiments with machine learning. So you see we had independent variables, so these attributes. We have a dependent variable, which was the next year absenteeism, and the baseline, which it was compared to, this is also used in human resources planning, is the current year's absenteeism. So the results, so we used several stock machine learning methods, random forest, gradient boosting, regression trees, linear regression, decision tree regressors, nearest neighbors, and support vector machines. And as you can see in, let's say, in mean absolute error, the there was basically no improvement at all. Most of the methods were even the same or even worse. So this was not very promising. But looking at some other methods, such as to RMSE, we can see that we can actually reduce it by 0.2, and this would mean that we actually can predict the. So that we actually can avoid larger mistakes at the cost of maybe more smaller ones. So not very promising here. Also, another test was to perform throughout the years in a sequential manner, so that we use data only available up to some point, and then perform the predictions. And what we can see here, that by increasing the time, oh sorry, so it's obviously touch sensitive, yeah. So with the ongoing time, when the data set, training data set is bigger and bigger, the mean absolute error actually decreases. So this obviously suggests that we could profit by using even more data. Also, another experiment, when this was done only for the last year. And here we included also data from previous years. So for a certain person, let's say for predicting for 2022, we also used another set of attributes for the previous year, or for even for previous 2 or 3 years. And again, here we can see that with increasing amounts of attributes in some cases, not always, actually the error is reduced. So again, this suggests that we could profit from more data. So these were quantitative results, which were not very promising. But especially for the company, much more interesting were these qualitative insights. For example, current year's absenteeism is by far the best indicator for the next year absenteeism. This is something that probably we all expected. Then there are some other things, like, let's say, absenteeism for a certain workplace or work position, which is also makes sense. And two things which are a bit tricky. So bonuses received and evaluation of the person, where we have to be really careful not to mix the cause and an effect. So if somebody really likes going on sick leave, if, let's say, I give him a bonus, will he be less sick next year? Probably not. So this is something that is correlated to the result, but there are probably not causal dependencies. Also, something that the company liked very much were explanations for particular cases with Shapley values. So this one in Slovenian. They actually really like this presentation. Also, they mostly, for, I don't know, 20 cases that were presented to them, they more or less agreed that everything makes sense. And they actually intend to use something in the future. So to conclude, there were some quantitative improvements in reduced errors, but they were quite minor, so not really that useful. Especially, it's not worth complicated to, let's say, replace the baseline, which is trivial to use. But these qualitative insights were quite useful. Possibly one of the main results of our work was that the data that were available to us is simply not strong enough. So we would need something more. We could, for example, use more granular data, so monthly or even weekly absenteeism and the other data, where we could actually do something in a temporal manner. We cannot do, let's say, time series analysis with, let's say, just four examples in a series, but we could, if we had, let's say, monthly or weekly data. We could also extract some qualitative temporal attributes, which again would help us even if we weren't doing the time series analysis. Obviously, including even more data would be very beneficial. So both, let's say, health data or social data for employees, but this can be highly questionable. Probably we wouldn't be able to get such data if they can even get them in human resources at all. And together with this, also some additional inclusion of domain knowledge, which at least for us was like pretty unknown field. So if you notice the results for, let's say, Slovenia and for the company, you'll see that in Slovenia in 2022 the average the mean absenteeism rate was 6%, and in this company it was, depending on the field of work, between 1% and 3%. So it is obviously quite a successful company in this sense. It's also one of the family-friendly companies, and also they have a series of in-house workshops to improve this quality of work and also to reduce absenteeism. And this is something that they would really like to be, if we could evaluate them, so the effect of their in-house workshops. But this is something which will stay in the pipeline for the future if they decide to actually go into a project with us. So thank you.
Okay, thank you. We have time for maybe one short question. Well done, please.
So just to clarify, the training instances were actually the yearly records for individual employees, right?
Exactly, yes.
So no data about the specific period, what was the reason and so on?
No.
Okay, I understand.
Yeah.
Then it means you are just guessing that this increase in 2021 was due to COVID, right?
Exactly.
Because one would expect maybe this should also show for 2020 already.
It was an increase in 2020 as well.
But not as much.
Not as much. Yeah.
Okay, but thanks. I understand.
Okay, before I do work for the next question, I would like to ask, do we have the speaker for the next presentation? Ah, you are here. Okay, I didn't know that. So yeah, then we have to move forward. Sorry. Thank you.
Yeah, thank you.
So the next speaker is Marko Jordan about smart challenge risk prediction.
Katera tipka je? Kako se da full screen?
Desno spodaj na. Levo. Ne, preveč. Še malo desno. Desno. Oh.
Okay. So first I'll say a few words about the Smart Change project. In this project, the aim is to develop artificial intelligence tool to predict future risk of cardiovascular diseases and diabetes. And then based on once we get the models, based on the outputs, the tool would then suggest lifestyle interventions to reduce this risk. It would recommend change. How much exercise do you need to do weekly? How differently should you eat? How much differently should you sleep? If it will tell you if you're too much under stress and so on. The target are the children and the adolescents, because this is the most important time, the most crucial time to recommend these changes, although the tool would be also available for the adults. And the current tools are mainly designed for the adults, so we are sort of one of the first to make it for the kids as well. So if I demonstrate what we're doing, so let's say this would be the main example ages. Let's say that we take a person aged 14. We predict what's going to happen at age 55 and then at age 55 we predict the risk. Now the reason why we have to go from 14 to 55 is because there are no models really at age 14, but there are at, let's say, age 55 in such ages. So yeah. Okay. Currently, we have two risk models. They are publicly available. One is for cardiovascular diseases, and one is for obtaining diabetes. So, in order to make such a model, ideally, we would like to have. Okay, first, I'll tell you what is longitudinal data. This means that each person has more than one timestamp of measurements. So you can imagine that instead of just measurements in 1 year, it has measurements in multiple years. And ideally, to go from 14 to 55, we'd like to have a person, and that person will have data points at age 14, age 15, 16, and so on till the age of 55. But the problem is there is no such data set. The data sets usually have the property that they're either for children or for adolescents or for adults, but you don't have the data set that would track the data from the children to the age 55. Or maybe possibly there are data sets, but it will be difficult to obtain them. So because we can't have only one such great data set, we needed to use multiple data sets. So in this version of the paper, we have 4 data sets. One is Slowfit, one is from Belgium, the third one is from Finland, and the fourth one is from Portugal. Now the Slowfit data set, you might remember, because in primary schools and high schools, we needed to do some tests, like run 60 meters, run 600 meters, jump as far as you can, and so on. And we actually use this data. It's also from the high school. So this is the Slowfit data set. In general, I'd like to point out, so the age ranges are, as I said, here you have children and adolescents. Here, this is the same here. It's also the same here, except that Young Finland study has ages from 0 to 60, but even in the Finland study, people are split to children and to older adults. So even here, you don't have really from 14 to 55 the data. And yeah, well, just to give you some idea, for Slowfit, we have 280,000 people approximately. Then for Belgian study, we have 18,000 people. For Young Finns, 3,500, and for Portugal data set 1,600. So first of all, because we have such a diverse, and maybe I didn't mention that the number of variables also is pretty different. Well, the point is that we have each data set measures something different. Okay, some variables are the same, but lots of variables are just completely different. So the issue here is, well, there are many issues, but first one issue is how to combine the data sets. So this will be a bit more technical part of the presentation. So first, there are many ways to impute the data sets, but the rule is like that. First of all, we impute only of each data set separately, and then once all the data sets are imputed, we combine those data sets together, and then we also have to do the imputation because not all the variables are present in each data set. So regardless of whether we do the imputation on each data set or on the whole data set, the process is the same. We have 2 sweeps. In the first sweep, okay, first we need to find the order based on which we will impute the variables. So first we find the variable that has the most data known, and then we find the second variable that has the second most data known, and so on. And this is the order, and in this order we will impute the data. But okay, first we have fully observed variables such as age, gender, height, and weight, and then first we use only these 4 variables and predict the first feature, impute the first feature, and then we add this first feature to the known, to the, to the imputed variables, and then we select the second feature, and then we still use all those 4 variables, but also add the firstly imputed feature. And then we repeat this process until all the variables are imputed. In the second sweep, once we have imputed all, once the data set is imputed, we fine tune it, because if you imagine just the first variable, we only have age, gender, height, and weight. But we also have more variables which are now imputed, so we will do the process of that, except that only, all the variables are now used for imputation, not just age, gender, height, weight, and the features already predicted, but here all are used. This is a bit more technical part. It's not completely crucial to understand it. So now we have let's check how much time it is.
You are at 10 minutes.
Okay, okay, so we have 2 approaches. One is population-based, the other is individual-based. So although both analyze the population, the population-based is more direct. So if you imagine we have a person who has 3 measurements at age when he's a child, and we want to predict him at age 55. In this population-based approach, what we do, we average the values, the 3 measurements, and then predict them in the future. Now, how we do this is actually we first need to normalize all the data. We first need to normalize the data. Look, the point is, the issue here is the following. Here in the blue, we have known data. In the red, the data is not known. And then in the blue is once again known, and in the red is once again not known. And the issue is how do we predict somewhere where the data is red, because we don't have any data points. If I just demonstrate, let's say that you have absolutely no data for people aged 80. How are you going to predict all the variables at age 80 if you don't have any variables at all at age 80? So what you can do is compute the means and standard deviations, and then fit this curve. This curve approximates the distribution, and then you assume, okay, if the child at when he was a kid, if he was like in 10% in the top 10% of this distribution, then also when he's older, he will be also in the 10% of distribution. But here in this population-based approach, the main point is, the main task is how to calculate the means and deviations, which I'll skip because and the other approach is just individual-based approach. And here we use 2 neural networks. One is from age 14 to 18, and the other is from age 18 to 55. The reason why this is so is because we have no data available. We have no people available. We have no people that would have data both at age 14 and age 55. This was not a problem for the population-based, because we just assume the distribution. Here we actually need the data, and we don't have this data. So we constructed instead 2 models. They are fully connected neural networks. The number of inputs is 27, which represents all the variables we have, and the number of outputs is 25, which means all the input features except age and gender. So these are the results. You don't need to analyze these results too much, because first of all, this is more like preliminary study, and secondly, look, I only showed these are the features, and this is the first neural network, the second neural network, this is the population-based approach. But the issue is here that there are 6 features, but actually we have 25 features. So then you have to figure out which how well the model works, that you have 25 features and you're predicting all of them. And the issue is also that, okay, how well do you know how you're predicting height? Because height is pretty much, let's say, constant between ages in 20 and 30. So, you know, on the one hand, you may be predicting height very well, but you're more focused on how well are you predicting blood pressure, how well are you predicting weight, how well are you predicting cholesterol, and so on. And it's not easy to compare all these features because they're just on different scales. But and the issue is also, okay, first of all, based on the bold letters, you can see that sometimes the population-based approach is better, sometimes the neural network approach is better. Yeah, I'd like to point out here that it's also the okay. I don't think this all goes to the future work. The issue here is, technically speaking, you should focus more on the variables that are important for the risk model. So, for example, if I don't know, okay, let's say that sleep isn't important, moral is. Let's say the sleep isn't important and blood pressure is important. So you need to, when you're training, you need to focus more on the blood pressure. And this would also be true for all the variables. So you can't just treat all the variables equally, and they're treated here equally. But the better way would be to have the weights so that the most important variables are have bigger weight. So for the future work, we only have 4 data sets. We need to increase them. The neural networks has to be more complex. Now we circumvented the problem of predicting from 14 to 55 by going with 2 separate models. But ideally, one would like to have only one model. I mean, only one model that would go directly from 14 to any age. The population-based approach and neural network approach also need to be combined. The data sets need to be adjusted based on the population, because Finland people are not the same as people from Slovenia, and so on. And we need to add new risk models for, okay, now we have cardiovascular and diabetes. So yeah, we also made a demo.
Sorry, there's no time.
Yeah, okay, this is just a screenshot of the demo. So you could specify all the variables and you would get something back. You'd get the risk back. Cardiovascular disease, this is the diabetes disease. This will show you how the each feature changes through time. Okay.
Okay, thank you. Any questions? Maybe one. Oh, there are 2 questions. Okay, Matthias, you were.
Okay, so you spent quite a lot of time explaining how you think the missing values and implication. So I understand that for older people, actually, you can move data available for, let's say, up to 20, 35 hours. And how many data were actually missing in for this early age?
For define early ages, which are the early ages?
So you had, let's say for Slovenia, you have data from, I think, 14 to 20.
Yeah.
Yeah. So is this a fully complete data set, or are there some data missing?
No, the Slovenska data set is fully complete because you're actually asking for Slovenska. You should ask me for other data sets like Finland. You know, they started tracking the data for kids, and then for older adults, they actually have different variables also. But also for the kids, it's like, yeah, I don't know, about, let's say, between 20 and 30% data is missing in each data set, except Slovenska.
That's quite a lot.
Yeah. And then also the variables change over. Yeah.
We have another question there. Yeah.
Thank you.
One.
So can you go to results across from the one before the last?
Yeah, I mentioned that it shouldn't focus too much on them.
So what I observed is that some of these predictions
or let's say reasonable, for example, height from
Yeah.
about 3 centimeters from 14 to 18 and from 18 to 55. But then some are quite good, for example, cholesterol.
Yeah.
How can you predict at the age of 18 what will be the cholesterol at the age of 55? And I'm just wondering, is it possible to somehow evaluate the quality of this prediction?
Yeah, well, the issue is that it's not perfectly, look, it's probably that here we have like just 4 subjects. The population-based approach needs to distribute in the whole range. So top 10% when you are young, it's top 10% when you're old. But if here you have, let's say, only 5 were people at age 55, and they all have similar values, the model will learn to predict the similar values. So probably all these people have similar values at such age. So how we would fix this is make bins of people aged 5-year bins and so on, between 15, 55, 45, and 50, so on. You get more people, and then you get more accurate results. So this is the issue.
Okay, we have to move forward. Thank you very much. Our last speaker for today is Matej Jelenc. Biomarker prediction in colorectal cancer and so on. So you will explain.
I didn't have the time to already put the presentation on here, so
fine.
just a moment. Okay, so first of all, thanks to everyone for waiting until the end. My name is Matej, and I'll be presenting the paper titled Biomarker Prediction in Colorectal Cancer Using Multiple Instance Learning, co-authored by Miljana, Anton, and Jitendra, who are currently not here. The structure of the presentation is the following. First, I'll talk a bit about the motivation behind this study and what drove us to pursue this topic, and quickly outline relevant related papers. Then I'll explain the terminology and the main methods behind this paper, and go through the entire pipeline of the experiment. And then in the end, present the results and finish off with some possible improvements of the experiment and potential further areas of research. So as the name, as the title shows, the main theme of the study was colorectal cancer, or CRC, which is the cancer of colon or rectum, and is currently the 3rd most common cancer, accounting for approximately 10% of all cancer cases, and is therefore an essential field for further research. Now, one of the main methods of diagnosing CRC is biopsy, where tumor tissue is cut into thin slices and analyzed microscopically on glass slides. Now, this process is very time-consuming and costly. So in recent years, a technology called whole slide images have been developed, which are basically scanned glass slides, and they provide an opportunity for computer analysis. So instead of manually checking the tissue with a microscope, this process could be automated with AI. Specifically, our study used deep learning to predict microsatellite instability, which is a key biomarker in CRC because it indicates defects in the DNA mismatch repair system, which leads to a high mutation rate within tumor cells and is essentially a critical factor in diagnosing CRC and choosing an appropriate treatment plan. Okay. So in terms of MSI prediction on the MCO dataset, there are two relevant related papers. One used a SWIN-T model with a fine-tuned pre-training classification model for MSI prediction, and they trained it on multiple small datasets. And when trained on the MCO dataset, it achieved average area under the ROC curve of 0.92. And then the second paper took a transformer-based approach and did a large-scale multi-cohort evaluation, which involved over 13,000 patients and achieved a negative predictive value of over 0.99 and a mean area under the curve of 0.85 when trained on the MCO dataset. Now, since the whole slide images are of best size, like one image is typically from 1 to 3 gigabytes in size, so it can be very computationally hard to process the entire image at once. So what is necessary to do is to divide it into smaller patches or regions. And a common method that addresses this type of issue when dealing with large data is multiple instance learning, which is a machine learning technique which operates on sets or so-called bags of multiple instances where a label is provided for the entire bag. So this is particularly advantageous in analyzing whole slide images because we have a label, we have only a bag or a slide level label, and we don't have patch level annotations. So we can treat the entire slide as a bag and then the divided patches as instances of this bag. Now, the basic overview of the pipeline of the experiment is as follows. First, we do pre-processing of the slides. In this part, we do the tessellation of the image into smaller parts. After that, we use state-of-the-art pre-trained feature extraction models, which essentially extract relevant information from each patch, which ensure that we don't need any patch level annotating. And after that, we use several aggregation techniques, which combine all the information from patches into a single representation, single feature vector that represents the entire slide, which is then used for further classification of MSI. Now, as mentioned before, the pre-processing part mostly involves just the tessellation of the slide, the bag of patches, but it also contains two optional steps. One is the removal of non-tissue or background patches, and the other is stain normalization, which ensures that all patches have, or not even patches, but all slides that are used for training have approximately the same color distribution, so as to, yeah, basically reduce color variation and improve model accuracy. Now, specifically, we extracted these patches at 1 micron per pixel, and each patch was of size 224 times 224, and this yielded around 3,000 patches per slide on average. Yeah, then after we tessellated and pre-processed the slide, we used, as I said before, state-of-the-art pre-trained feature extraction models, which were trained on large data sets and can capture rich and discriminative features that are necessary for classification. Uni, Prof, GigaPath, and Ficon are all based on the vision transformer, with Uni and Prof GigaPath having the Dino architecture and being trained on 100 million and 1.3 billion images respectively, while Ficon has the iBot architecture and was trained on 43 million images. And the last feature extractor that we used was CTranspath, which is basically a CNN backbone in combination with a string T model, and was trained on 15 million images. Now, after we extracted these feature vectors, we used aggregation techniques to combine them into a single representation. Now, standard aggregation techniques are like max pooling or mean pooling, and they're pretty straightforward. However, we decided not to use such approaches because they are limited in the sense that they lack trainability. And the aggregation methods that we used were ABMIL or attention-based pooling, which assigns a weight to each feature vector and then ultimately computes the representation of the entire bag. Now, on the other aggregation technique we used was DSMIL, or a dual stream aggregator. Now, the dual stream aggregator is made up of 2 branches, and one performs in a similar fashion as the attention-based aggregator, basically using attention to compute a feature representation of the entire bag or slide, while the other branch first classifies each instance to it classifies each instance and then uses max pooling to find the critical instance, then combines the computed feature representation of the bag and the critical instance to get one single representation. And the last method that we explored was Transmil, which is a transformer-based approach, and it differs from the first two mainly in the fact that it also tries to take into account the spatial relationship between different patches and how far apart two distinct patches are, or how close. Now, at the end, we have the we get the aggregated feature vector, and the last part, which is the classification, is relatively simple. It's just passed through one or more fully connected dense layers, and then the output of the last layer is passed through an activation function. Specifically, we used sigmoid function to get a probability value between 0 and 1, which then indicates the likelihood of one slide being MSI positive. And then we can also make a binary decision by choosing a threshold. We used 0.5 for the threshold. Now the data set we use in the study is, of course, the MCO. This was conducted by the Molecular and Cellular Oncology Study Group from, I think, 1994 and 2010. They systematically gathered tissue samples and clinical data from over 1,500 patients, which resulted in more than 1,500 whole slide images, CRC. Now, the entire data set amounts to around 3 terabytes of data, For this paper, we didn't use the entire data set, only a part of it, just due to the sheer size. And we used 996 full-slide images, of which 242 were labeled as MSI and 754 as MSS, which is microsatellite stable. Then we did a basic split where we randomly excluded 20% of the testing data, and then the rest was divided into 5 equally balanced parts for cross-validation, which ensured robust training and relatively accurate evaluation. So these are the results. Hope that it can be seen well, the numbers, but the best result was achieved with the combination of the dual stream aggregator and the Prof gigapath feature extractor, reaching an area under the curve of 0.91 and standard deviation of 0.01. And the best two feature extraction models when using tension-based aggregation were Python and Uni, with standard deviation of 0.01 and area under the curve of 0.91. And then for the transmill, the most successful feature extraction model was again Prof gigapath, achieving area under the curve of 0.9. Now, in conclusion, we had a pretty good results, doing a notable achievement when comparing to the previously mentioned studies. If we compare results, the results are comparable with the paper that used the Swinty model. Even though we did not use any tissue classification model to further focus only on specific patches. And we also gained a 6% improvement from the transformer-based approach, even though we used a smaller data set. Now, for future work, there are several possible avenues or things we can do. The most straightforward one is to use the entire data set and just increase robustness and hopefully accuracy. We also plan to do multi-cohort evaluation and take use of other publicly available data sets. Another thing that could potentially increase performance is fine-tuning the pre-trained models, specifically for the MSI prediction task. Since these were very general histopathology models, we could also incorporate a tissue classifier, which would further induce the number of relevant patches and only focus on tumor tissue patches, which would first reduce computation and secondly reduce the noise and make the model better. Another thing is the development of advanced aggregation methods, which can better capture different patterns, nuances. And lastly, we want to do a multimodal approach. So essentially, for this study, we only used whole slide images, but we also have clinical data for each patient. And it would be interesting to see if a combination of both could perhaps lead to better results and more interesting correlations and patterns. That's all from me. Thank you for.
Okay, thank you. Yes, please.
Yeah, so thanks for the presentation. I was wondering if you have all your methods seem to be pretty close, right? So you do any, let's say, statistical analysis?
Yeah, we did the Wilcoxon rank test. Yeah. And it produced a p-value of 0.446. The problem is that we only had 5 folds, so the there wasn't a lot of data for the statistical tests in that sense. And yeah, it's as we kind of expected, there wasn't any significant difference between the results in that sense.
So you're using a sample
For now, no, not yet. Maybe in the future we could use an ensemble. But yeah.